Okay, thanks for coming. So I think um, I brought a student from the both class, one from 10 a.m. and 4 p.m. And thankfully I made a synchronization on their uh, lecture schedule. So I think for both classes, yeah, we can start our discussion from this slide, locality. So I try to finish it by midnight tonight. Okay, I do my best. Okay, please remind what we had like a few hours back in our previous lecture. We have we basically see what's the basic idea of paging. And paging is kind of good idea if we can manage the issue regarding page table. I mean, yeah, paging will be really great if we can access the page table in an efficient way. But as we all see, the size of the page table is pretty large compared to the amount of the memory that we can afford in a architecture level. So there's an issue, but we have seen a pretty nice idea of TLB, which is a kind of a cache of the page table, by which we can hold a pretty large page table. And page table become large because we make each page small. And as we have a small page, I mean, if the amount of the memory given to each unit to amount of the memory given to each memory management unit becomes smaller, I mean, we have a better freedom in allocating memory, and also we can avoid page fragmentation issue as well. So, I mean, it'll be always good if, not always good, but it'll be really good if we can have a small pages. But as the size becomes smaller, the number of the entry that should exist in a page table increase. But as we have a TLB, we can nicely resolve those issues and take both advantage of having page table and also high-speed memory access as well. And so TLB is kind of a mandatory device in modern computer architectures. And we briefly see why TLB works by memory access example. Please remind what we had for this one, this example, and also in this example. So these two examples show you that even though maybe throughout the program execution, a program can access multiple pages and different memory addresses. However, within a short time period, program tend to access very limited region of the memory. And this characteristic of a program is known as locality. Yeah, here we can save memory access because memory access of an ordinary program tend to have a temporal locality and spatial locality. Temporal locality here means that if a program accesses memory address X, suppose that we just call the memory location as an X, then temporal locality means that the program is very likely to access X again in the near future. I mean, program tend to access same memory address repeatedly. Why? Guess why? Because human write a program in that way. Why? Human think in that way. Human think in that way. We kind of make a sequential logic. We kind of make a sequential logic when we write a program. So we update the same variable multiple times to make some to implement some complicated computation. That's how human brain works. So you heard about magic number 7? Or you heard about magic number 7? It's kind of very old story in computer science anyway. Magic number 7 is that if the number of the input of a function count the number of the input variable of a function. And if the number exceeds 7, programmers tend to have very difficult time in managing that. And this is actually true. This is really actually true. You can conduct small psychology experience. If you memorize very random number and the number of the numbers exceeds 7, then it'll be really hard to have all those numbers at the same time in your mind. That's how human works. So we tend to use a few number of, like a 3 or 4 number of the variable at a time and accumulate some computation on them to implement some functionality. That's how human brain works. So program written by a human tend to have a temporal locality. Another thing also similar to the temporal locality, but different thing is that is a spatial locality. So if a program accesses memory at address X, then it is very likely to access X plus D, where D is a small number, which means that, yeah, if it accesses a memory location, then it is very likely to access memory nearby to the previous access address in the near future. And this also the same reasons behind here. So, I mean, if there are 3 variables intensively used in a certain logic, then those 3 variables will be closely located in the memory. So programs tend to have a temporal locality and spatial locality. Another reason for spatial locality is like an array. I mean, even though we have so think about an array. What is an array? Array is a kind of an abstraction of a certain variable. So when we manage multiple variables, yeah, we cannot really manage them if we cannot abstract them in a simple manner. So array, even though there are a lot of the variables are behind, but we kind of treat each element in a pretty much the same way and repeat some computation over different indexes. So once we manage it, once the program operated on an array, then typically, yeah, we continuously reference some related, consecutive indexes in a row rather than jumping from here to there in a random manner. So some sequential pattern appears in program execution. So thinking in this way, suppose that you are computer architecture and there's some application program running upon you and you receive some requests from the application program. Then you as a computer architecture kind of know what will come in next step based on the history of the memory accesses. So it's it's not fully predictable, but it's largely predictable. So that is the locality of a computer program, and TLB exploit these characteristics so that it make kind of a prediction. So if you just access on X, then I will save a VPN and PFN for this X because you application program is very likely to access the same memory location or other variable in the same pages again in near future. That's how TLB works. Okay. And locality also concern when we, as you study the computer system. I mean, I think you already heard about this when you learn computer architecture, I guess. This is the phenomena that caching idea, why the caching idea is basically working. And caching appears in a different layers of the computer systems, and all those caching idea works when some locality exists. And yeah, this is the case for page table and TLB. Yeah. Okay, so in designing, okay, so TLB, so here we explain, we kind of know what's the reason the TLB is, or for what reason TLB is working and save memory accesses. So another issue I want to remark before moving on is that yeah, there is a trade-off relationship between the size of the TLB and TLB access speed. Why? Because TLB is implemented in a hardware level. So if it is a if it contains many entries, then the logic for managing those entries will become larger. So the length for the signal, I mean the length of a circuit that manages TLB become larger. So I mean it'll spend much time for delivering, transferring some signal to each unit. So as the TLB become larger, access time will take longer. So there's kind of a trade-off there. So I mean, if we have a very small and compact TLB, then access on few entries will be really speedy. But here the limitation will be that limitation is that, I mean, if your program access many pages frequently, then TLB is not big enough to afford all those paging information at the same time. So it later, I mean, the hit ratio cannot be, hit ratio kept high in a certain level, so it'll later hurt the overall performance. So if we increase the size of the TLB, then we can afford many page table entry at the same time in TLB, and that save on memory access time, but access time on TLB entry itself become slightly longer. So it should be carefully designed. Yeah.
Isn't TLB a physical built-in memory?
Yeah, so yeah, TLB is a physically built-in computer architecture. You can think of it as a part of the cache memory. But even though it is embedded in a computer architecture level, I mean, compared to the ALU or core unit of the CPU, TLB kind of memory kind of stuff, memory units like a TLB or caches are relatively far from the core unit, and the clock speed for accessing them are relatively slow. I mean, CPU is quite fast. I mean, they are amazingly fast. So, I mean, maintaining this type of the storage devices require much longer access time comparing to the register. So that's kind of an issue. 네. 우리가 근데 워낙 칩 안에 있으면 되게 빠를 것 같잖아요. 근데 칩 안에도 여러분이 혹시 봤는지 모르겠지만 거기서도 이제 완전 그 인싸 유닛들이 있습니다. 걔네들끼리 꽉 팩돼 있고요. 그다음에 거의 뭐 저기 뭐 예, 신도시급으로 이렇게 있거든요. 캐시들 뭐 거리가 있어요. 근데 이게 같은 인스트럭션 사이클 안에 들어와 버려야 돼요. 그러니까 이게 신중하게 디자인을 해야 돼요. 이게. Okay, let me move on. Okay, so this is a repetition of our previous slide that where I introduced TLB first time. So far everything is nice, but in explaining this slide, I think some of you made a question that some step in this algorithm is not quite well explained. And guess which step? So here the missing part is that I just smoothly moved on, but here big missing link is that how can we update the TLB? How can we update the TLB once we receive a new page frame, physical frame number is given? And this is a kind of a tricky issue. So I will explain how this works for next few slides. 내가 잠이 많이 오나 봐요. 말이 잘 안 나오네. Okay, handling TLB miss. I mean, if TLB hit, for the case of the TLB hit, everything is fine and happy. This is exactly how we expect the system to go. So this is kind of a sunny day situation. But what's for the TLB miss? And who will treat the TLB miss? That's kind of a first issue to address. Okay, what if computer architecture find there's no proper, corresponding entry for VPN in TLB? Then how the next? So what's the next step for that? And there are basically two approaches for handling TLB miss. First approach is by computer architecture. We call it as a hardware managed TLB. And the other approach is a software managed TLB, and this is taken charge by operating system. So let's check first hardware-based TLB. So when TLB miss happens, then within an instruction cycle, computer architecture recognize this issue, and then what? Computer architecture access page table which reside in a memory and get the corresponding and searching for the corresponding page table entry and bring the information to the TLB. And all those things are managed by hardware. So what will be the benefit for hardware managed TLB compared to the approach of using software part? Since it's implemented by hardware, it'll be faster, obviously, right? So it's kind of good. TLB miss sacrifice memory access time. So compared to the TLB hit cases, it'll spend far more runtime costs. So if it can be managed by computer architecture, then relatively, the time cost issue will be moderated by a fast hardware access. But what will be a limitation if we treat the TLB miss by hardware? Then here obvious problem is that, since computer architecture to handle TLB miss, there should be a very strict rule for managing page table. We need to acknowledge exact location and exact size and exact format of the page table to the hardware, or it's upside down. Computer architecture request operating system to make a very operating system to place page table in a only fixed location, and there are not much freedom for managing its structure. So everything is prefixed by computer architecture. If we allow computer architectures to access page table directly, it's a kind of a problem, especially when your system have a pretty large amount of the memory, and so that more sophisticated algorithms should be used for managing large number of the page table. But if your system is really small and nothing is really non-trivial in managing page table, I think this approach will work pretty nice manner. 조금 더 이야기를 하자면, 페이지 테이블이 나중에 엄청 커지면 무슨 문제가 생기냐면, 이것도 나중에 스와핑까지 배워서 나오는데, 페이지 테이블 아까 보니까 4메가 넘어간다 그랬잖아요. 근데 아까 페이지 크기가 얼마였어요? 4kb였어요. 그러면 페이지 테이블도 메모리 올라가야 되는데, 사실 그 문제를 제가 이야기를 대충 하고 넘어갔었는데, 그게 사실 쉬운 일이 아니에요. But let me repeat in English. So in previous example, remind that at 10 a.m. or 4 p.m. today, I told you that typically if we use a 32-bit machine, a page table for a single process become like a 4 megabyte of size, require 4 megabyte to store all the data. But remind that in that system, one page use only like a 4 kilobyte, which means that to store page table, we need to have a lot, like 1,000 pages are needed for a single page table. So managing that large page table require more sophisticated management scheme. So in such a cases, hardware managed TLB have many restrictions. But if the size of the page table is really small, then this will be a nice idea. Okay. So what about the software managed TLB? For software managed TLB, when TLB happens, yeah, TLB miss can be recognized by computer architecture. Then just the architecture delegate this handling job to the operating system by how? By raising trap, not trap, raising exception, raising exception. Then operating system, I mean, if operating system already registered corresponding exception handler, then handler will be dispatched, and then handler recognize for what reason it was invoked, and if it was due to the TLB miss, then what? Certain piece of the code that you wrote will work to resolve this issue. So page table, so sophisticated page table management job can be implemented easily by this approach. So architecture raise exception in the middle of the instruction execution due to the TLB miss. Here, the important thing is that, I mean, it happened inside of an instruction cycle. So when TLB miss exception occurs, then it means that still the instruction execution was not accomplished, right? So PC count doesn't change. PC count remain as it is, and exception happens. Then the operating system, I mean the exception handler part of the operating system will be invoked, and it recognizes the issue, and then what? Bring the, I mean, searching the entry in a page table, and then what? Store, I mean, update the TLB to hold the requested page table entry. To hold the, I mean, update the TLB to hold the requested TLB entry, page table entry. So here you immediately you can easily recognize here that then in order to implement this, we need to have a special instruction for operating system to update the TLB. And that instruction should be implemented as a privileged instruction, right? Which can be only executed under the kernel mode. And there should be some instruction by which operating system can directly touch TLB. It's a kind of a strange thing, by the way. Why? I told you that the original genuine goal of the computer system is to make a TLB transparent, so that for software side, TLB should be invisible thing. But as we delegate the management of the TLB to the operating system, we need to open up some channel to the kernel. Kernel is also kind of software part as well, by the way, to manipulate these hardware devices. It's a kind of complicated thing, right? Yeah, but it's unavoidable. Yeah. And then what? So, okay, TLB now updated and hold the page table entry information for this instruction, which raise a TLB miss in its first trial. So after finishing the exception handler execution, then what? Computer architecture go back to the original context where exception occurs. Then I told you that PCs remain the same, so instruction cycle restarted. Instruction cycle restarted. 예, 무슨 말이냐면은 인스트럭션 사이클이 아까 전에 실행이 다 인스트럭션 사이클은 아토믹하죠. 컴퓨터 아키텍처가 인스트럭션을 인터프리트하는 건 아토믹해요. 아토믹하다는 건 무슨 말이냐면은 제로를 나셔. 예. 그러니까 이거는 미안합니다. 제로 원이에요. 그러니까 인스트럭션이 완벽하게 실행이 되거나 아니면 인스트럭션 안 실행되거나 둘 중에 하나밖에 없어요. 중간에 서는 게 없어요. 근데 이제 인스트럭션을 인터프리테이션, 그러니까 실행시키다가 뭐가 문제가 생기니까 TLB 미스가 난 거예요. 그러니까 전체 시스템 입장에서 인스트럭션이 실행이 안 된 겁니다. 아직. TLB 미스가 다 리졸브 되고 나서 그럼 어떻게 하냐? 다시 인스트럭션 시작. Okay. So in architecture retry executing the instruction, and this turn surely the expected TLB entry exists in TLB hardware. So it will not raise a TLB miss again, and so it definitely TLB hit happens. So instruction will be successfully done. 사실 이것도 사실은 아닙니다. 이게 무슨 이슈가 있을 수 있냐면 인스트럭션 중에서 메모리 레퍼런스를 여러 번 하는 인스트럭션이 있을 수 있어요. 요즘은 그런 인스트럭션 x86만 하더라도 약간 여러분이 그 x86만 하더라도 시스크 머신의 느낌이 남아 있습니다. 리스크 시스크 할 때 그러니까 굉장히 복잡한 인스트럭션들이 남아 있어요. 근데 그 인스트럭션 중에 어떤 애들이 있느냐면은 메모리를 통짜로 복사하는 이런 인스트럭션들이 있을 수 있어요. 몰라요. x86가 그런 게 있는지 내가 확실하지는 모르는데 이제 옛날 아키텍처 중에 이렇게 메모리를 통째로 복사하는. 왜냐면 이거 한 번에 쫙 복사하면 빠른데 그런 일들이 많잖아요. 근데 그런 게 하다 보면 어떻게 하다 보면 잘못하면은 페이지 여러 개에 걸쳐 버릴 수가 있어요. 그럼 TLB 미스가 계속 발생할 수 있어요. 예, 그런 거는 그래서 그런 일이 생기지 않게 아키텍처 레벨에서 이제 그런 사이드 이펙트가 안 생기게끔 조정이 돼서 설계가 됩니다. 그리고 OS에서 만약에 그걸 해결을 한다고 하면은 OS가 굉장히 조심해서, 그러니까 이런 로직은 굉장히 조심해서 짜요. 왜냐면 한 끗 틀리면은 굉장히 끔찍한 일들이 생길 수 있기 때문에. 그다음에 불필요한 게 하나도 없게. 왜냐면은 이거는 굉장히 자주 실행되는 코드라 가지고 그 퍼포먼스가 굉장히 크리티컬한 영향을 주니까 이런 건 굉장히 신중하게 보통 어셈블리로 짜죠. 어셈블리로 필요한 인스트럭션. 사실 여러분 지금 이 교과서에서는 요런 좀 복잡한 이슈들을 그렇게 많이 다루지 않고는 있어요. 마지막 챕터 가면 아마 좀 나오긴 할 텐데 난 그게 좀 좋다 생각합니다. 그 옛날에 작년까지 제가 썼던 공용책 같은 경우에는 이제 이 내용들을 설명할 때 이 모든 이슈가 다 나와요. 진짜. 그러니까 여러분이 공부하기 큰 그림 잡기가 너무 어려워. 그러니까 좀 알면 큰 그림 잡고 가는데 모르면은 이게 너무 디테일한 것까지 이게 레벨이 막 들쑥날쑥하단 말이에요. 그래서 할 얘기는 많고 재밌기는 한데 나도 이거를 그 전체적으로 좀 퍼스트 스킴을 일단 쫙 한 다음에 다시 가르치면 좋겠다 이런 생각을 많이 했는데 지금 이 책이 그런 스킴 하는 데는 너무 좋아요. 근데 또 이 책의 단점은 또 이게 너무 약간 생각해 볼 거리가 좀 있는데 약간 좀 빨리빨리 가는 경향이 또 좀 있습니다. 근데 우리 학교 상황에서는 요런 요 수준으로 이게 다 위스콘신 메디슨에서 이걸로 가르치는데 뭔 말을 해요. 그래서 일단 이걸로 공부하고 나중에 여러분 방학 때 그 제가 이미 링크 올려놨는데 그 스탠퍼드에서 또 쓰는 XV6 커널 갖고 보는 그 OS 책이 있습니다. 그 XV6 커널 그 코드 보면서 하는 거 있는데 그걸로 한 번 더 공부하세요. 예. 그러면은 거기 보면 이제 TLB 핸들하는 거 이런 거 코드 다 있을 거예요. XV6. 나도 XV6 갖고 제가 학부 다닐 때는 뭘 했냐면 나초스라고 자바 위에서 올라온 OS 있었어요. 그게 이제 교육용 OS인데 자바 위에 올려놓은 OS가 있었는데 밉스 머신 위에 올라가 있는데 그땐 제가 학부 다닐 때만 하더라도 세상에 자바가 나왔는데 사람들이 너무 자바가 좋은 거야. 너무 자바가 좋은 거야. 난 지금도 그렇게 생각하는데 자바는 정말 진짜 어드밴스된 랭귀지거든요. 네. 나는 인류의 성취라고 생각합니다. 자바가. 농담이 아니라 자바가 인류의 성취예요. 인류의 성취입니다. 정말 노블한 그런 랭귀지거든요. anyway, 그래갖고 사람들이 자바에 너무 경도돼가지고 모든 걸 자바로 만들던 그런 유행이 있었어요. 나 OS 자바 만들 그 약간 실수죠. 그래서 나는 학부 때 그거 갖고 이제 숙제하고 막 그렇게 했어요. 근데 그건 아닌 것 같고 시스템 코드는 C나 이렇게 요즘 이렇게 해야 되는 건 맞습니다. 그래서 여러분이 제가 지금 이제 여러분한테 줄 숙제는 너무 많고 시간 없으니까 좀 조심하고 이렇게 잘 설계해서 줘야 되는데 일단 그래도 한 번은 커널을 봐야 돼서 XV6에다가 뭐 시스템 콜 추가하고 이런 걸 한 번은 숙제를 내줄까 해요. 나도 안 해봤기는 한데 XV6 갖고는 한번 내가 해봤거든요. 혼자 여러분이 하는데 어려움이 없을까 해가지고 나 좀 요즘 이렇게 만져보고 있는데 괜찮은 것 같아요. 예, 그래서 예, 그래서 한번 숙제할 건데 그때 이제 보면은 그냥 코드 읽으면 읽어져요 다. 페이지 테이블 보면 페이지 테이블 이렇게 하는구나. 그런 식으로 한 번 더 공부하세요. 지금 이 책은 조금 되게 큰 그림만 그립니다. Okay, TLB entry. So what kind of information needs to be stored in TLB entry? I mean, the attribute that page table holds needs to be also represented in a TLB as well, because it's a kind of a cache, right? Cache. So typically TLB entry has VPN information, PFN information. This is kind of an essential, right? I mean, these tools are mandatory thing. And also valid bit is also mandatory, right? Valid bit is also mandatory because TLB is a kind of a hardware stuff. So we do not really, we cannot recognize whether some garbage value is in or meaningful value is in if we don't have a valid bit. So valid bit is true, it means it's not garbage. But if somebody want to erase the data, instead of filling them with the 0, just to turn off the valid bit, then architecture recognize this is a meaningless thing. Okay, that's a valid bit. And protection bit is also needed because computer architecture offer this type of permission control for better utilization of the memory. So this is kind of needed. I told you that read-only permission, I mean, read-only bit is read-only or read-write bit is essential for sharing memory, sharing pages across multiple processes. So this is an important thing. Dirty bit is also important, but this is relevant to the swapping issue. So please hold on. And more information can be also contained in TLB as well. I mean, it is a computer architecture who designed the frame, right? So computer architecture also is aware of what kind of information needs to be stored for page table, and that information should appear as well in TLB entries. 예, 이게 다 컴퓨터 아키텍처가 하는 일이니까, 그러니까 컴퓨터 아키텍처 이렇게 설계를 해놓은 거니까. 그러니까 이 아키텍처에서는 이 프레임 사이즈를 쓴다 하면 페이지 사이즈가 그거에 대해서 결정이 되는 거고, 이 프레임에 이런 정보들을 붙일 수 있다고 돼 있으니까 페이지도 그걸 갖다 쓰는 거니까 TLB에서도 그걸 고려를 하는 거죠. 예, 그러니까 이건 뭐 다 일관되게 돼 있겠죠. And typically architecture have a TLB of a computer architecture have a 32 entries or 64 entry, and if it is a big, 123 entries exist. They're relatively small, right? Once we compare it to the size of a page table. Yeah. But and also I told you that searching on TLB happens in parallel because these are implemented in a hardware level. So, I mean, it's not the computer architecture does not iterate over different entries, but simultaneously the searching happen on multiple entries at the same time. So to reduce access time on TLB information. I think this is last slide. Okay, I have 2 more slides to go. Okay. Another issue for managing TLB is what should we do when there's context switching? Context switching. Thinking in this way, suppose that our TLB entry have these information, and TLB was used for a while for executing a certain process, and context switching happened, and CPU is loading a new process. What would be an issue? Yeah, this mapping should be invalidated, right? Because another process have its own VPN, and this VPN should be mapped to a different PFN. But if a TLB just hold these information, and it will be surely wrong, but not only wrong, but also this is dangerous. Why? If we TLB offer PFN information of other processes, then yeah, information can be leaked through TLB, and isolation will be broken. So then how can we protect this issue? And so it make a protection problem. So how can we resolve this issue? Yeah, so
turn off the value.
turn off the yeah, I mean, so one easy way to resolve this issue is that flush all entry at the moment of the context switching. So one process is just, when before dispatching a new process to a CPU, maybe as a last step for storing the information for the older process, maybe operating system needs to flush by invalidating all entry, so that for new no TLB information remain when a new process is dispatched. Okay, this is a kind of a one easy way for resolving this issue. Yeah, so flushing can be made it simply by turning off all the valid bit of every TLB entry. And here the issue is that, so if it is made it this way, what will happen right after context switching? Yeah, series of the TLB miss happen essentially until some amount of the necessary information are all loaded to the TLB cache. And I told you that TLB miss is a costly compared to the ordinary situation. And if at the early moment series of the TLB miss happen, then responsiveness of the system will be slightly hurt at the context switching moment. So this contribute to a cost of the context switching as well. 여러분, 제가 컨텍스트 스위칭 설명할 때 그때 코스트 중에 뭐가 있냐 했을 때, 그렇죠, 보이는 코스트도 있지만 안 보이는 코스트도 있다 그랬죠. 그 중에 하나가 지금까지 쓰던 캐시 날아간다. 이것 똑같은 거예요. 사실 L1, L2 캐시 날아갈 가능성 크죠. 프로세스 바뀌면 똑같은 논리로 TLB 날아갈 수 있어요. Okay, so it's kind of an issue, especially when TLB is a big. If a computer architecture provide large room for TLB, but if it is always flush at the context switching, then TLB is less utilized. Utilization of the TLB will be very limited. So if we have a large TLB, then we need to have some mechanism for avoiding this issue. And here the idea is put process identifier to TLB. Yeah, this is a kind of a way to resolve this issue. And here process identifier is sometimes coded as a address space identifier. So address space means virtual memory of a certain process, right? So you can just think it as a process identifier as well, or a proxy of the process identifier. By how? We here add another entry here and say that address space ID, ASID. Then as a pair of the VPN and ASID, or you can also think of it as a process ID, then computer architecture can distinguish VPN over different processes. So this means that we don't really need to flush everything at context switching, just remain as it is, because we give ASID, PID together with the VPN. So no confusion occurs, even context switching happens. Then what? A new process is loaded. So if there is nothing, no TLB entry for new process exists at the moment, then essentially TLB miss will happen. But what if the new process do not really use many pages? Then larger portion of the TLB will remain. And maybe eventually the old process will be dispatched again. Then it is likely that the old TLB still remaining there and can be used. Okay, so this make multiple process readily share TLB, so it kind of moderate the cost for context switch. Make sense?
So it's not for the current process, but
for the future, to come back. To come back. 적절한 비유가 떠오르지 않습니다. Okay, so we kind of see many issues for this part, but here the last piece is that for updating TLB for placing a new information, we need to kick out one old entry. I mean, in order to, here we brought a new page table entry information, and we want to keep this one because this is kind of fresh one. So this one is expected to be used frequently in next few steps, but there's no space. So we need to kick out one old one, but which one? That's kind of an issue. And that type of decision making is generally known as replacement policy. Replacement policy. This happens also frequently in many different issues in computer system. 이 replacement policy라는 것도 굉장히 제너럴하게 나와요. 그래서 여기서만 나오는 게 아니라 계속 나오고, this issue will be more intensively. We will check this issue in more detail when we discuss about swapping, because replacement policy matter much at the swapping. Yes, swapping 할 때 이거에 대해서 좀 더 할 겁니다. So your textbook doesn't really tell anything about this, but it just defines this problem. So here the problem is which entry to evict when TLB is full and new entry must be installed. 어떤 거 킥아웃 하면 될까요? 이름이 상진 학생. 누구를 킥아웃 하면 될까요?
가장 안 쓰는
거. 가장 안 쓰는 거라기보다는 가장 앞으로 필요 없을 것 같은 거. Maybe the one that we expect most usually is in future, but we cannot accurately predict future. 그럼 어떻게 해야 되지?
우선순위 낮은 프로세스.
우선순위 낮은 프로세스. 그건 맞는데 그걸 어떻게 하면 좋을까요? 그거를 생각해 보면, 여러분 미래를 예측하는 제일 좋은 방법은 뭘까요? 그렇죠. 과거를 보면 historic based. So many algorithms, many heuristics are invented for dealing with this problem, which use the previous history. But issue is that this should be very quickly happen. I mean, this decision making should be very lightweight, because still be aware that everything that we are concerning here happen inside of an instruction cycle. It should be very lightweight. 그래서 멋있는 걸 쓰면 쓸 수 있겠죠. 근데 그러고 있을 시간이 없어요. 그냥 간단하고 심플한 퀵 하지만 뭔가 좀 그래도 어느 정도는 말이 되는 그런. So decision should be made it to minimize the TLB miss rate, and also while not incurring much time overhead. Okay, that's kind of so it's a multi-objective problem. So this is generally this type of problem is known as cache replacement problem, and we will see this issue multiple times in later part of this course as well. At there we will see more. We will have more discussion on that. And at this moment, let's just check that one nice idea is evict the least recently used one. Evict the least recently used one. 가장. So we count the last moment that when a TLB entry was actually referenced. Suppose that we keep some kind of a timestamp. 시간 다 찍어놔둡시다. And we look over all the entry there and trying to find the one that have all this timestamp, then edit that. Why? Because it is likely that this one is not really used anymore. So it's not a perfect it's not a perfect algorithm, but this one works nicely in many practical situations. And you will see that there are more, we will have more discussion on that, and there are more alternative or more extended version of it. But LRU is generally known as pretty nice solution in this situation. LRU라는 말을 많이 씁니다. 네, LRU. 저는 이걸 일상적인 용어에서도 많이 씁니다. 뭐 이렇게 하다가 이거 LRU로 하죠. 뭐 이렇게 LRU로 하죠. 네, LRU로 하죠. 예, 여러분 예를 들어서 축구 풋살 찰 때 밀어내기 할 때 어떻게 하면 됩니까? LRU로 합시다. 이렇게 하시면 됩니다. LRU로 합시다. 뭐 이렇게. 예. 뭐 근데 축구할 때 LRU 하기는 좀 쉽지는 않아요. 유식을 어떻게 이해를 해야 되냐 싶기는 한데 보통 축구할 때는 이제 가장 마지막에 골 넣은 사람이 나가죠. 네. LRU로 하게 되면 뭡니까? 제일 골 넣은 지 오래된 사람이 나가죠. 그러면 이제 좀 갸우뚱하죠. 네, 같은 돈 내고 축구하는데 이렇게 하면 안 됩니다. Or if you're not really confident about anything, just take a random one, because random is not perfect, but this is a safe. Random selection is safe because it doesn't have any bias effect, so it doesn't really involve any side effect. But designed algorithm easily have a side effect if it doesn't carefully consider different situations. Yeah. So if nothing is clear, then random is a pretty nice option to take. Okay, that's it. Good. So I just reaches the end of chapter number 19, as I remember. Yeah. Chapter number 19까지 왔습니다. And this is so by this slide is your midterm coverage. Yeah. And note that your midterm coverage include not only the lecture slide, but things that you can find in your textbook, even the part that I do not cover. 내가 설명 안 한 거 일부러 찾아서 시험 문제 몇 개 낼 거예요. And exercise questions. Yeah, exercise question도 낼 거예요. And the thing that's not in the textbook, but I covered in my lecture, that's also a part of your midterm exam. And what about the programming things, as you have in homeworks and usually given through the tutorial for your homeworks? 그건 시험 범위일까 아닐까요? Yes, it is. Yes, it is. Yes, it is. 근데 뭐 그거 공부한다고 되겠습니까? 그렇죠? 공부한다고 되니까. 근데 간단한 코드를 써라 혹은 간단한 코드를 읽어라 하는 문제가 나올 수 있습니다. 네, 근데 막 뭐 신텍스를 본다거나 막 뭐 어떻게 틀리나 뭐 이렇게 하는 게 아니라 그 컨셉을 이해하고 있는지에 대해서 좀 물어볼 수는 있습니다. 근데 나 아직 시험 문제 안 냈어요. 네. And once you go to the classwork page, let me put the web browser here. Let's go to the course web page. Yeah, this is me 6 years back. Here, yeah. What I want to tell you is that here, once you go to the previous year's instance, and you can see the problem set for the midterm and final. Yeah. Here, and also once you go here, you can also find where it is. Here, midterm, yeah, midterm and final. Obviously, I mean, we use the different textbook, so coverages are different and the contents are different, but please check what kind of you can, but I mean, yeah, I think you can get many meaningful information by checking these questions. 요거 문제 있는 거 그대로 나올 가능성은 좀 적겠죠. 하지만 뭐 어떤 식으로 문제가 나올지 여러분이 좀 이렇게 예상하는 데 도움을 줄 수 있지 않겠습니까? 네. 그다음에 특히 이제 작년 거 보시면은 이게 작년 건가? 아, 예. 왜 없지? Sorry. Problems. I will fix the broken link. Yep. Yeah, 이런 거. I think last year the midterm exam was programming exam. Then you better check the final exam. 내가 이게 리팩터링을 했나 보다. Final problems. Yeah. You see that this shape as like a PPT slide, right? Yeah, you will be given the problem set pretty much the same style as this one. 네. 작년에도 온라인으로 시험 쳤거든요. 네. It'll be given in this form. 이거 근데 이때는 학기 전체가 그 범위였어요. 그래가지고 사실 여러분이랑 좀 많이 다를 것 같다. 네, 그러니까 사실 문제에서 건질 건 많이 없을 거예요. 네. Anyway, that's it for today. Thanks for joining in this late night makeup class, and I wish you good luck for preparing for the midterm exam. And I will come to you by more detailed instruction for the midterm. And if I have more news, then I will contact you through the Slack.